So, chapter 5 is atoms and atomic structure. Yeah, and this is atomic structure part 1. We're going to do atomic structure part 2 later when we get to it. All right, so we're looking at a hydrogen atom and then a helium atom. So the first thing is, what are these made of? Well, the hydrogen atom, it turns out, is made up of, we have actually 3 different kinds of hydrogen atoms. And so one hydrogen atom has 1 proton, 1 electron. Just write P, E. This hydrogen atom we call the H1, so we put a little thing there, or we spell it out, hydrogen dash 1 or hydrogen 1. So this is one type. This is the most common. It turns out that greater than 99.9% of all hydrogen atoms are this type of hydrogen atom. There's another one which is called H2. And H2 has 1 proton, 1 neutron, and 1 electron. And so the difference between an H1 and an H2 is that this one has a neutron in there to create him. This one's called H2, like this, or deuterium. They actually give a special name, deuterium or hydrogen 2. This is, they don't usually give special names to, the different types. I mean, it's still hydrogen. For example, even though this one, there's a very small percentage, but if you had a glass of water today, you consume some deuterium. So if you consume deuterium, or actually ate food, I mean, there's water in food or whatever, and in fact, we consume this all the time, the deuterium. Can you tell the difference between water with a hydrogen 1 and water with a hydrogen 2? You can't tell the difference. Their chemical properties are exactly the same. And so chemically, these are the same. Chemical props are the same. The difference between these are in terms of physical properties. Physical properties are different because this one just weighs more. In fact, deuterium, although it's not exactly twice as much, it's close to twice as much. And so it's a heavier hydrogen atom. Why is it so much heavier? The reason it's so much heavier is because of the neutron. In fact, the protons and neutrons weigh about the same. The electrons turn out to be a lot lighter. And you don't have to have the masses because these masses are not exact. These are in terms of mass units. But, what we say about the, let's see what the book says before we get into it. What we say about the mass of the proton is it's about 1 U. And a U is this. So the masses for the proton, it's about 1 U. And for the neutron, it's about 1 U. And for the electron, it's about 2,000 times lighter. So it's about 0.005 U. So the electron is quite a bit lighter. The proton and neutrons, they weigh about the same, although they aren't exactly the same. And the electron is quite a bit. And so here, this whole hydrogen weighs about 1 U. This hydrogen 2 deuterium weighs about 2 U. roughly. And so that's about the level you need to know it. You don't have to have the precise numbers, although there's much more accurate, much more precise numbers known for the masses. In fact, we could get a lot of sig figs on the masses for these particular things. Okay, there's one more hydrogen atom, and this one's a little different though. This is H3. Now H3 has one proton and two neutrons, and that's why it's going to have about a mass of 3. Now that's where this number comes from. This number we call the mass number, and the mass number is not the mass because the mass is about 3U. This is an exact number. The mass is not an exact number. This number comes from the number of protons plus the number of neutrons. That's what we call. So I'll break it down in a minute. And then this will have one electron, the same. Okay, this one is called tritium. Again, this gets a special name. So chemically, tritium is the same, except this. It's an unstable atom. And so this is what we call radioactive atom. So we separate like chemical properties from radioactive properties. So chemically, all 3 of these hydrogens behave the same, but one of them is an unstable atom. A radioactive atom is unstable, and eventually it breaks down into other atoms. So this is tritium. Now, helium only has one type of atom. Only one type found in nature. What nuclear chemists try to do is they try to mess with the proton and neutron and try to make other types of atoms. The old chemists used to try this because for a long time, chemists were trying to transmutate lead into gold. They wanted to figure out a way, how can you convert lead into gold? And so that was one of the big things. But they were never successful because you can't convert lead into gold by chemical properties. However, with nuclear reactions, you can transmutate from one element to another element. Not necessarily lead into gold, but other ones. And so there could be some radioactive, what we call radioactive atoms of helium. Those radioactive atoms, sometimes we'll call them radioactive nuclides or radioactive isotopes. But isotopes are reserved for more. These are called 3 isotopes of hydrogen. And so the isotopes are the same atom but just different mass. Same element of this hydrogen, but different mass. When I say element, I'm talking about atoms or nuclides. Nuclides is just another word for a single atom with different masses. And so here are the 3 isotopes of hydrogen, H1, H2, and H3. For helium atom, there's only one type of atom that is isotope or nuclid. Nuclear chemists will call it nuclid. Found in nature, nuclid usually refers to just one atom of that particular type. Now, this helium is going to be helium-4. This turns out to be quite stable, as is. This is going to consist of 2 protons, 2 neutrons, and 2 electrons. And so the mass, about how much does a helium-4 weigh, roughly, in terms of U? Now, what is a U? A U is just a unit that's quite convenient. I'll define what a U is in a minute. But it's going to be about 4U. All right, we can easily convert from grams to U. It's going to be about 4U. It's not exactly 4U. Like a proton doesn't weigh exactly 1U, and a neutron doesn't weigh exactly 1U. And so I want to talk a little bit about the mass, since this is one of the things that we can easily characterize about atoms, that is mass. Here. And so the U, this is called atomic mass units. And atomic mass units are defined in a special way. The definition of the U is based on a carbon-12, we call nuclide. This is just one atom of carbon-12, and it's a specific atom because carbon-12, actually there are two isotopes of carbon that occur in nature. There's carbon-12 and carbon-13. And then there's also carbon-14. But carbon-14 is special. Do you know what's special about carbon-14?
It's radioactive.
It's radioactive. And carbon-14 is formed by cosmic radiation bombarding carbon, stable carbons. And so typically when we think about carbon in nature, we think of carbon-12 and carbon-13 because how much of our body is made up of carbon-14? Very, very minute amount of carbon-14. And so, anyway, carbon-12 is one of the atoms in there. And in fact, it's the most abundant. It turns out it's more like 99.8% of all carbon is carbon-12. And so carbon-12 is, if you have graphite or if you have amorphous carbon, it's cheap and it's easy to obtain in fairly high purities. But anyway, the definition of the U is based on the carbon-12. And so one carbon-12 atom is defined as weighing exactly 12 U. And so this is an arbitrary definition, right? This is a totally arbitrary definition. So somebody said, okay, this carbon-12 atom weighs exactly 12 U, and then we can weigh everything else relative to it. And so a carbon-12 atom, what does it consist of? The carbon-12 atom consists of 12 protons and 12 neutrons. And, actually not 12 protons, sorry. 6 protons, 6 neutrons, and 6 electrons. And so we combine all that, and that comes out to exactly 12 U. That's how it's weighed. Now, this is going to have interesting implications because this is an arbitrary definition. And so pre-1950s, 1960s, pre-1950s, 1960s, the U was defined differently. Based on oxygen-16. Oxygen-16 is the most common type of atom in oxygen. And so in the 1950s and 1960s, what they said is this: one oxygen-16 weighs exactly what do you think they arbitrarily defined that to weigh? 16 U. Well, that's a different definition, and that means that all of the masses prior to the 50s, early 60s are no longer used. In fact, if you go to an old book, you'll see that the masses are different. So for example, if you take a look at our book and see what a hydrogen atom weighs, and then you look at a 1950s textbook and see what a hydrogen atom weighs, they weigh different amounts. Even though the units are the same, they're both U, they just decided to change. Now why did they decide to change the definition? Oxygen's plentiful, right? But there's a problem with oxygen. If you're working with oxygen, oxygen is a gas. And so it's a little bit more difficult to work with gases than it is to work with solids. And so this is where the switch came from. It also has to do with technology, because one of the ways we weigh the atoms, now how do you weigh an atom? Well, one of the ways we weigh atoms is we have to vaporize the atoms into a gas form. And so it was very hard to vaporize atoms off the surface of something like graphite. You know? But now with lasers, it's very easy to vaporize atoms off the surface. Laser, what we call laser ablation, it just knocks atoms off the surface. So we could do that. Well, anyway, this is just talking about the masses so far. So we know that, you know, hydrogen atom weighs less than a helium atom, but, you know, hydrogen atom is bigger than a helium atom, even though it weighs less. So that means it's a less dense atom. You know, helium atom is a more dense atom, and things are packed together more tightly. Now, why would things be packed together more tightly? Well, let's look into the structure a little bit more deeper. When we look into the structure a little more deeper, then there's a certain arrangement of the stuff. But before I do that, let me talk about one more thing. Who discovered these particles, you know, in the atoms? And so, you know, we should talk, you know, how do people figure out what atoms are made up of? Okay, so we talk about the discovery of the proton. Discovered the proton, you know, this is a guy who discovered the proton, but you can read about this if you're interested. And so you don't have to know how they discovered the proton. It's okay. The neutron, the same thing. You could read about it if interested. The electron, the book wants you to know who discovered it and how they discovered it. Do you know who discovered the electron? Well, J.J. Thomson. When? Around the 1800s. And how he discovered the electrons, and you know, people have noted electrons before J.J. Thomson, but J.J. Thomson in the 1800s, people have noted the electrons because of these special rays like lightning, other rays, but J.J. Thomson figured it out. It's a fundamental part of all matter. And so we'll talk briefly about this. How he discovered it is by using the CRT. You know what CRT stands for? CRT. You know, if you had an old television, the old television had a CRT tube in it. The old televisions. It was way before plasma, although a similar thing. Way before LED. It's a tube television. And the CRT stands for cathode array tube, or Crookes tube. People call these Crookes tube. We used to have an operated Crookes tube, but it's broken. So otherwise I'd show you what the Crookes tube looks like. Let's see if this came back wrong. So I'll show you. What this looks like. But basically, you know, what it is like a lightning bolt. You know, when you have a lightning bolt, Lightning bolt is like a beam of electrons, right? And how does a lightning bolt form? A lightning bolt forms when there's what we call a potential or voltage difference between one point and another. In other words, there's an electrical imbalance. We can create an electrical imbalance and we can create a lightning bolt, but this is a very controlled lightning bolt. The way you can get a very controlled lightning bolt is by doing this. We have a vacuum tube here. If we can suck out most of the gas out of here, we won't get this lightning bolt that's going in all random directions. We'll just get a lightning bolt that goes smoothly across like this. That's because there's not much gas in there. If you put a lot of gas in there, you're going to get a discharge that's going to look like a lightning bolt. In fact, we could do that without the tube. And so you put a low pressure gas, which we call a vacuum. It doesn't have to be like a super vacuum. Just a moderate vacuum in here.
Would you like anything?
Okay, sorry.
Pretty much all the cathode tube.
Maybe this is alright, this is taking too long. Sorry. Let's do this one. There's a homemade cathode ray tube. It says,
Hey guys, this is Beaver King Simon. So today I'm going to be showing you my homemade cathode ray tube project. This video will be split into two parts.
Okay, I'm going to fast forward. I'll just tell you the setup here. And so first off, we need this kind of voltage difference. And so this is what we have here as a power supply.
Yeah.
This is briefly shown. And so we need just a piece of metal in there. It could just be like a metal nail would work, or a plate. Plates are very effective. So if we have a metal plate here, it's metal. And then we have another piece of metal here. Now we could do this in the open air. What we do is we hook this up to a power supply. And what the power supply does is it creates an imbalance in charge. And what the power supply does is it tries to suck electrons away from one atom and then force the electrons over here, because electrons have a charge. The electrons have what we call negative charge on there. They have a -1 charge. The protons have a +1 charge. And so if we hook up a power supply here, the power supply sucks in electrons, say, this way, and then forces them out this way. But the protons are left behind, And so what happens is, the protons and the electrons balanced each other out. One was negative, the other was positive. But if you're sucking out the electrons this way, then what happens here is this plate is going to build a positive charge here. And over here, this plate is going to build a negative charge. Okay, when the positive and the negative charge gets high enough, then the electrons can actually travel through space here and create a discharge. It's much more complicated than that. We do need the gas here. What happens is the gas turns into what we call a plasma. So we'll have a plasma there. Plasma is going to be a partially ionized gas. Partially ionized gas is going to have free electrons that can travel here. And so, to make a long story short, the electrons, eventually the electrons will build up here until we get a discharge. When we get that discharge, and we need, for a cathode ray tube, we need like 1,000, 2,000, depends on the pressure inside here. We have something called the breakdown voltage. And once the voltage gets high enough, that is, there's so much electron built up here that it's just going to discharge here to neutralize this. And so these are going through space here, or through, actually, not through empty space, these are going through the gas in the tube. So this is going to be sealed up in the tube here. Okay, this beam of electrons is called the cathode ray. And that cathode ray, you know, so we got a beam of electrons, we got a metal. And so they're thinking that where do these electrons originate? These electrons originate from the metal here. They're originating here. Being transferred over here. Now, the reason they thought that the electrons were a fundamental part of all matter, I mean, not just metals, is this. Can change the metal but what we end up with is the same cathode rays. So what they inferred from this is that all atoms contain electrons. It doesn't matter what the atom is. That all atoms contain electrons. Okay, so if you change these are called electrodes, you know, piece of metal here. But the electrode, it doesn't have to be a metal. It could be like graphite. Graphite conducts electricity also, non-metal. And we would generate cathode rays too. And so it doesn't matter what the electrode material is, as long as it conducts electricity. Now, non-conductors aren't necessarily going to work here. And so
Actual cathode ray tube was built using a wine bottle and some stainless steel wire. I drilled a hole into the side of the glass bottle carefully using a glass drill bit and inserted a wire bent in a half circle shape. Then I secured it with hot glue to make sure it was vacuum proof. As you can see, I made two of them and they each have the wire at different lengths down the tube. To create a vacuum inside of the wine bottle, I just attached a hose bar into the vacuum hose and slipped a rubber O-ring over it. When the vacuum is pulled, the rubber O-ring sucks down onto the bottle and it just seals itself. This way there is no epoxy or glues needed. Now it's time to power up the cathode ray tube. To do this, we need to attach some electrodes to the terminals of the Wilbur radiation transformer. Next, we simply attach one of the other ends to an exposed piece of the hose bar and the other to that wire we added into the wine bottle. Now I turn on the variac and slowly, carefully turn up the voltage. As you can see, a beam of electrons, also known as a cathode ray, appears. It glows a bright purple color in my case due to small amounts of nitrogen and oxygen that are still left in the tube.
this is similar to a neon light tube. Neon light tubes are cathode ray tubes.
Now, that time I was just running the tube on an AC current. So this time I'm going to add in a high voltage diode to make it a half-wave rectified current and see the difference in the beam. Now that we have that diode, let's power it up. As you can see, part of the beam that is glowing is only on one side of the tube. Last time it was on both sides, and there was a dark space in the middle. Now I'm going to demonstrate the magnetic deflection property of cathode ray tube. Since it is made of electrons, it can be influenced by a magnet since the electrons have a negative charge. Here I have a few magnets, and one side is marked with tape. When I put one side of the magnet that is marked onto the beam, it bends around to the right. When I put the unmarked side to it, it bends around to the left. Now I'm going to switch around the electrodes so that the electricity is flowing the opposite way. Now this time the dark space is on the other side. When I hold up the marked side, now it bends around to the left, and the unmarked side bends around to the right. So depending on which way the electrons are flowing, they take a certain path around the magnet. Now I took out the diode and I'll show you the deflection of the beam when it's running on an AC current. As you can see, the beam appears to split around the magnet. Now, I told you earlier in the video that this is going to be split into two parts. The second part is going to go over the more technical aspects, describing why the beam splits and why it switches directions. If you're interested in that, I'll be using slow motion to analyze the cathode ray tube, and I'll show you some scientific formulas that
right, so you can see on one electrode he used brass, on the other it was a steel wire. And so it didn't matter the material, you still generate the same beam of electrons. And so based on that, again, people are thinking that all atoms contain electrons, so that's a discovery. J.J. Thomson was able to pull a higher vacuum. His vacuum wasn't that high, and you could see a lot of deflection and curvature in that beam. If you had a really good vacuum with very few atoms in there, the beam would have been straight from one end to the other. Okay. Now, if you had more gas in there, like a weaker vacuum, then you'd need a higher voltage, and it would look more like a lightning bolt. As it progressively gets higher and higher, and more gas inside the container. And so that's the discovery of the electron. Now, how about the mass of these? How do you weigh these things, you know? So let's talk about that next. So this is the discovery. The mass what we call subatomic particles. The subatomic particles are the proton, neutron, and electron. And mass single atoms. Single atoms are called the nucleids, right, or isotopes. Well, one of the things that you notice is that when a particle is charged, it's deflected by a magnetic field. So for example, when he brought the magnet to the beam of electrons, did you see how it curved around? Well, electrons, are they light or heavy? Electrons are very light. What if you had a beam of charged particles that were heavier? So if you have a beam of charged particles that were heavier, would the amount of deflection be the same, greater, or less by a magnet? It's the same size magnet. The amount of deflection would be less. You know, if you are a heavier particle, and you have the same charge, then you're going to have a lot more what we call inertia. That is, it's going to be harder to change direction. Versus a light particle can change direction very rapidly. And so based on that, physicists came up with a way to weigh single atoms. So for example, if you could shoot not a beam of electrons, a beam of electrons is easy. You can buy electron guns, they're cheap, these cathode ray type things. But instead, you form a beam of atoms. Now, how do you form a beam of atoms? You can form a beam of atoms in different ways. For example, helium's already a gas, so there's a whole bunch of atoms, and then you just flow helium. And then you have to charge them. Well, if you have helium atoms, how can you charge it? So one, you force helium atoms to go across a path here, and then you charge them. There are two different ways you could charge helium atoms. One way you could charge helium atoms is by using an electron gun, like this cathode ray. You know, just shoot electrons at it, get it to charge. So a helium atom might pick up an extra electron. If it picks up an extra electron, we call it an ion. Now, if it's charged, then you keep passing it by a magnet. When you pass it by a magnet, it's going to get deflected. And based on the deflection, the angle of deflection, that'll tell you the mass. So you can use some physics to figure out the relative mass. And so this is what's done. What's done is you take a sample of carbon-12, like graphite, and then you hit the surface with a laser, which vaporizes. Now, two atoms are going to vaporize off the surface of graphite. Carbon-12 and carbon-13. So a lighter one and a heavier one. Their masses don't differ that much. Then you shoot them out a little hole, and then you charge them by doing different things, electron gun, whatever. And so you have charged carbon-12 and carbon-13. And as the carbon-12 and carbon-13, they're going to pass by a magnet. As they pass by a magnet, the carbon-12 is going to be more deflected, the carbon-13 is less deflected. So they actually are going to impact the surface at two different spots. Now, where they impact the surface, you place a detector there to count the number of strikes. And so let's say the carbon-12 strikes here, the carbon-13 strikes a little bit later. Now, where the carbon-12 strikes, you set it on the computer. You set that at exactly 12U. And so if the carbon-12 hits here at exactly 12U, then you use a little bit of physics to figure out how much the carbon-13 weighed. And so based on that, we can determine the mass of the electron, we can determine the mass of the proton, the neutron, we can determine the mass of atoms, single atoms. And so this is called a mass spectrometer that we use. And so let's take a look at a mass spectrometer action for animation here.
Begin with a simple analogy to get across the most basic principle of the mass spectrometer. Three balls of equal size with different mass. The lightest ping pong ball straight down, straight through. Somewhat heavier golf ball straight down, straight through. And the heaviest, the snooker ball, straight down, straight through. The hairdryer would be put on at this point, blowing air from right to left. Look at the deflection of each ball. 5 for the lightest, the table tennis ball, 3 for the golf ball. And what about the heaviest? The snooker ball has the least deflection, scored just 1. Conclusion then is the ball with the greatest mass is deflected the least. In the mass spectrometer, the magnet plays the role of the flow line. Look at the labels: a heater, element to create a vapor, an ion accelerating field which gets the positive ions streaming from left to right towards the magnetic field, the detection field at the top right there. The entire mass spectrometer is enclosed and is evacuated. There are no air particles inside so that the beam of ions has a free run. No air particles to strike. In the copper color you see 2 rectangles. One at the bottom is the electron gun. It's an element which is heated and generates electrons which are attracted towards the capture plate, the larger of the copper-colored rectangles. This produces a beam of fast-moving electrons. Entering at the bottom left there, you see the sample represented with green spheres. If it's not already a vapor, your sample will have to be heated to create a vapor. We'll have our sample might be ions, atoms, or molecules. If it is atoms or molecules, we have to change the atoms or molecules into ions. This is the role of the electron gun. The electrons will knock off 1 or more electrons from the atom or molecule. When an atom or molecule loses an electron, it doesn't affect its mass, as electrons have negligible mass. But it will create a particle which is a positive charge, or 2 positive if it loses 2 electrons. Adjacent to this field is a positive plate. And the moment positive ions are produced, the positive plate will repel from left to right towards these blue spheres, which represent plates with slits in them. And the role of the slits is to focus the beam. Watch now as the green spheres turn to red, brown, or yellow, creating ions of different mass and charge ratio. You'll see the yellow spheres represent the ions with the greatest mass and charge. They're deflected the least, whereas the brown, they're deflected the most. They're the ions with the lowest mass and charge ratio.
We don't really have to get into the physics later, but basically we just put in atoms of different mass, and then the mass spectrometer just segregates them. And so these would be the heaviest, the least deflected. This is a magnet here. These would be the lightest. Now what we do is we do the calibration steps. So let's say this was carbon 12 here. Then we just assign this position carbon 12 using the computer, this calibration, exactly 12U, and then we can measure everything else relative to that. This is a way we can measure the masses of the atoms themselves. This is called mass spectrometer. It really is. All right, so what we'll see is we're going to have different masses of atoms. And so let's take a look at your book here. A second. I'll get the PowerPoint back up. Going here. But these mass spectrometers are very high precision instruments. These can weigh, down to very minute masses. And so let's take a look at some of the results from the mass spectrometer here. So what did I say hydrogen 1 weighs about? Get this focused. About 1U. But if you feed that into a mass spectrometer, we can get the mass much more precisely. In fact, if you look at the mass here, hydrogen 1 weighs 1.007825031U. Do you think that's an exact number? No, the only exact number for mass will be for carbon 12. If we look at what a carbon 12 weighs exactly 12U. Why? Because somebody defined it that way. In what was it? When was it that they used this one? Oxygen 16 in the 50s and 60s. Everything prior to the 50s and 60s will have a different mass because they set the mass spectrometer, like when oxygen 16s went through the mass spectrometer and they struck the detector, where they struck the detector, they defined that as exactly 16U. So if oxygen 16 is exactly 16U, then that means everything else gets bumped, right? And so if you look at this mass table, this is from your book, compared to a mass table from an earlier book, they're different. And so be careful. That goes the same for the periodic table. If you look at an old periodic table, all these numbers in black here are different than this new periodic table. And so you have to be a little bit careful there, depends. Now, how many hydrogen atoms, how many types of hydrogen atoms did I say there were? Three. One's missing here because I see hydrogen 1 and I see hydrogen 2. Hydrogen 2 weighs almost twice as much, or actually it looks like just about twice as much, close to it. But where's hydrogen 3? Hydrogen 3 is not on here because it's not what we call really naturally occurring. It's a radioactive. The radioactive ones are not usually listed here unless it's only radioactive, like uranium. And then I said there's carbon 12, carbon 13, and carbon 14. But carbon 14 is missing here. We know the masses of a lot of these, like tritium, we can get the mass. Carbon 14, we can get the mass as well. But carbon 14 is relatively long-lived as far as radioactive isotopes go. But one of the questions that comes up is, how can we predict? Do you see a pattern here? Maybe the pattern is that there's always two different masses of two different types of each element. Is that correct? And maybe a radioactive one. Is that a pattern? See, okay. It looks like maybe there is a pattern because I said helium-4. I discounted this one. I shouldn't have. This is helium-3. But helium-3 is not that abundant, so I completely ignored it, unfortunately. But this one, if we go to beryllium, beryllium has only one type of atom. And so all atoms in a sample of beryllium found in nature are 100% beryllium-9. There are no other. And so we go on to carbon, there are 2. Nitrogen, there are 2. Look at most of these favors 1. Do you see that? So for example, nitrogen 14 is a lot more favored than nitrogen 15. If we go to oxygen, oxygen 16 is more favored than oxygen 17, but there's one more. Oxygen 18. And then we're back to fluorine. Fluorine is, there's only one. You see this is the percentage. 100% of all fluorine found in nature is fluorine 19. And then we go to sulfur. There are 3 for, actually not 3, there are 4 for sulfur. And then there are 2 for chlorine, there are 3 for potassium, there's 7 for mercury. So do you see a pattern there that we can use to predict, how many? No. In fact, this is part of the scientific method. Part of the scientific method is, are you going to come up with a hypothesis? Can you come up with a hypothesis how many types of atoms you're going to find and what their percentage is going to be? What's your hypothesis? What is the hypothesis in this case? If you think about it, that's an extremely difficult question, I think, to come up with a hypothesis. It just doesn't make sense to come up with a hypothesis, because look at the numbers. And so the first step in the scientific method is not to come up with a hypothesis. The first step in the scientific method is to observe. So we observed this. And so what have people done? Well, what people have done, this is a different branch of chemistry. This is nuclear chemistry. And this is not a branch that we're going to delve into much. Maybe one chapter at the end of the semester. And then a very brief survey of nuclear chemists. Chemists are not necessarily interested in this. You know why? Because this. Did you taste the difference between hydrogen and deuterium this morning? Do the water molecules with deuterium behave differently? Maybe they're flammable or something else? No. And so the reason that chemists are not interested in this per se is because they don't impact chemical properties. This is why these are all oxygen. This is oxygen, this is oxygen, this is oxygen. They all have the properties of oxygen, just one weighs more than the other. That's it. They have all the chemical properties of oxygen, I should say. And so this is why we don't call it different. This is, for example, is not oxygen, and this is not some other symbol, some other name, because they're going to behave differently. No, they behave the same. All right, let me stop. Oh, actually, we still got a little bit more time. And so how were these masses obtained? Can you tell me how did they measure the mass? Can you take a single atom and place it on balance? Is it possible? No, it's impossible. There's no way you're going to measure a single atom. But can you measure single atoms? Yes, you can. How do you measure it? What instrument do you use to measure it? You use what's it called? What's that instrument called? It's similar to cathode ray too, but cathode rays is another word for electron beam. And so it's not cathode ray. Cathode rays are the electron. It's called a It began with an M-A-S-S, mass, like a meter, mass meter, but we add something before the meter. Mass with an S. Nobody wrote it down? Nobody remembers? No, that's short-term memory. That was like a couple of minutes ago, 5 minutes ago. Mass spectrometer. Mass spectrometer. We just watched the YouTube here. I'll just show you. There are a bunch of YouTubes on mass spectrometer. Mass spectrometer is a huge instrument in chemistry and nuclear chem. This is the simple explanation of the mass spectrometer. The mass spectrometer is much more sophisticated than what they're showing. This is like a cathode ray tube here. But the mass spectrometer gives an output. That output is on the detector plate. Do you see what they call this? They call it the spectrum.
That's what means the detector.
The spectrum. And so let's flip back to your book here. So your book does not show mass spectrometer, but your book does show this. So there's no figure of a mass spectrometer, but there is this figure. What is this figure here? Do you see that, the bar graph? this bar graph is called the mass spectrum. This is of neon. So the mass spectrum of neon, this tells us how many neon atoms, how many types of neon atoms are found. 3 types. Could you have predicted that? No, you don't know the pattern, you don't know, although I'll tell you the nuclear chemists are trying to figure it out, the nuclear physicists are trying to figure out. They want to be able to predict these types of things, of course, right? If they know the theory well enough. But this would be nuclear, this is different than quantum mechanics. Although they use quantum mechanics, this is particle physics. Very small particles. But anyway, we get back to this. Well, how do we know there are 3? Because that's what's observed, that's facts. And there are 3. And it turns out, which one do you think is the most common? These are the masses, the relative masses. It's close to 20, not exactly 20, close to 20. This one is the most common because that has the most strikes on the detector. And so from the mass spectrum, we get 2 very important things. From the mass spectrum, we get the mass to a high degree of precision and accuracy, and we get the percentage. And so this table was generated from the data collected from a mass spectrum. The mass spectrum was obtained from the mass spectrometer. All right, I'll stop here. Let's take a break.